you doing? My name is Alessandro Trinchera, and today we will discuss together another important astrophysical topic, the cosmic microwave background radiation, or abbreviated the CMB. In our discussion, I take the opportunity to introduce and explain my paper on the CMB, recently published by the Journal of Physics Conference Series, in which I calculate a CMB as originated by cosmic dust grains in the interstellar medium and in the intergalactic medium. Please consider it as topic of discussion in your comments. Any comment is, of course, welcome. For more information, please check out the link in the video description. Is the CMB really a relic radiation of a nearly and hot universe in the past? Is the Big Bang theory a red theory, although it is well accepted in the public opinion? Well, it might be one possibility, but it is not the only one. Both the CMB and the expansion of space, declared to be directly associated to the cosmological redshift and to the Big Bang, are not supported by observations at all. Indeed, Big Bang, inflation and space expansion are pure mathematical arguments. Guys, please be always critical in whatever you do and read, and don't take any theory for granted. Mainstream science provides only one side of the story. Just be aware that the universities in fields of astrophysics and cosmology don't have any interest at all to question a wrong mainstream model as long as they obtain funding for supporting just one cosmological model. Alternative theories don't have any financial support. They are not even mentioned in the lectures or in the scientific books. This makes harder for anyone who has a new emerging idea to discuss alternative theories. Academia and all journals related to them ignore, reject and push down all these new arguments. In this mainstream system, scientists mention the current cosmological crisis as if it were an external problem, something not related to the university. But they are themselves the main part of this crisis, as they are part of a conservative and business-oriented system and environment. The CMB is defined as the last Thomson scattering surface of a hot universe in the past. In simple words, the CMB was the first wall of photons that departed from this hot primordial universe. The universe was in the past dense and hot, and it started to expand adiabatically and to cool down. During this phase, we recognized the presence of electrons, protons, plus some other atomic nuclei. We can focus on electrons and protons, which are really important. Indeed, in any thermal system, and also in a hot universe, the temperature is also associated to a kinetic energy. Electrons and protons could not combine to form neutral hydrogen in these high energetic states. During the expansion, the temperature cooled down, making possible the combination of electrons with protons to form neutral hydrogen. This process leads to the emission of photons equal to the bonding energy of the hydrogen atom equal to 13.6 electron volt. So, we have two scenarios. The created photons scatter elastically with free cooled-down electrons, and at the same time, the photons can potentially photoionize the neutral hydrogen. Theoretically, we could see a loop without end, recombination and photoionization. However, it is stated that photons were able to escape the so-called decoupling from matter. The only process able to allow this process is the two photons transition. Basically, in order for the decoupling to succeed, the hydrogen atom could only generate two distinguished photons, each with an energy smaller than 13.6 electron volt, or rather not enough to photoionize the hydrogen atom over and over again. This process is much unlikely, but the only one possible that could decouple photons from matter in a nearly universe. How can we observe the CMB today? That's really an interesting point. According to the mainstream theory, such as the Big Bang, these photons escaped from the early universe and stretched out due to the expansion of space. So they travel throughout the cosmos in time and space, close to the Big Bang to our position now, totally undisturbed. They stretched out their wavelength due to the expansion of space. They kept their blackbody behavior as they escaped from a hot universe in thermodynamic equilibrium. But how is it possible? So, how is it possible that the SMB photons travel undisturbed in the cosmos? Don't they get absorbed and re-emitted from other atomic nuclei? The hydrogen left behind expanded faster than the speed of light, and doesn't this blackbody curve get distorted? For this reason, as well, how can astrophysicists see the properties of a hot universe at the moment of decoupling if the SMB photons must interact with matter and radiation on their journey? Astrophysical objects related to the Big Bang behaves always magically with respect to the foundations of physics. So they introduced the magic inflation, the dark energy and so on, just to protect the Big Bang theory at any cost. One cost is the destruction of the foundations of physics. Moreover, let's take for valid for a moment the assumption that the universe expanded and also that the decoupling took place. If the universe is almost 14 billion years old, as stated, and we are now in this old age, and a CMB was emitted in the past, how could these wavefronts of CMB photons hit the Earth during its journey from all directions? I would expect that these wavefronts should have passed the Earth or our local group if the space really expands. What are we really talking about? The only possibility for mainstream science is that these photons are bouncing through Thomson scattering in a closed universe. In this case, we would not see an almost homogeneous CMB map with tiny fluctuations, but a really distorted map with high fluctuations. But it is not the case. We measure a CMB map having tiny temperature fluctuations and a black body. For this reason, we should investigate another region for the CMB. Might be the case that some targets in space are generating this radiation in thermal equilibrium. On the left, we can see the anisotropies of the CMB map. On the right, it is possible to observe the structure of the local universe with colors inverted, with all astronomical objects distinguished for different redshifts. If we overlap the CMB map to the map of the local universe, we obtain this image. In principle, the galaxy clustering and the molecular clouds made of H2 and dust found in the map appear to correspond to the average fluctuation temperatures in green, whereas voids correspond to the low temperature fluctuations in blue. However, it is not always true, as some low fluctuation zones might also be found in correspondence to clustering zones, especially in the center of the map. That zones at high temperature fluctuations, yellow and red, correspond to punctual astrophysical sources undergoing a Sonayev-Zeldovich effect. Accordingly, we are concretely observing a closer source of thermal radiation than expected in a cosmological explanation. If we overlap the CMB map with the X-ray map of the local universe in order to highlight the location of these astronomical sources with respect to the temperature fluctuations, the peak of these CMB temperature fluctuations seems to correspond to high-energetic astronomical point sources in the sky. On this regard, the Sonayev-Zeldovich effect can be equally explained in a CMB originated due to a local radiation in the intergalactic medium and the interstellar medium. High-energetic electric photons, during the interaction with CMB photons, do not recognize any difference between a microwave photon generated in place or a microwave photon coming from the background. The inverse Compton process takes similarly place and leads to the distortion of the CMB map even with the local source of CMB radiation. As visible in the map, the light is clearly polarized along preferred spatial directions, and it is fully independent on the spatial origin of the CMB, as the radiation can only reach the satellite position by crossing the Milky Way, across the Lagrangian point L2 in the Earth proximity. By folding back the map into a spherical shape, the meaning of the orientation of the polarization takes shape. This clearly associates the polarization map to our galaxy. What does it mean? It means that the local source of the CMB cannot contrast the influence that galactic magnetic fields have, and we observe a continuity in the distribution of the orientation of the emitter source in the map. Hence, the source of the CMB should be local. In order to produce a blackbody spectrum, for definition, the photons of light require to interact with absorber-emitter objects on the cosmic highway. We schematize these objects as targets in space. So we are looking for the diameter of targets in equilibrium with the redshift starlight necessary to produce a thermal radiation at 2.725 Kelvin. The mathematical and physical boundary conditions for performing the calculations are the following. A starlight source emits a spectrum which, without the absorption lines, can be approximated to the Planck distribution. It is received by a terrestrial observer with different perceived frequencies. The constancy of the spatial distribution of targets and free electrons in the intergalactic medium. Photons of light interact with both on the cosmic highway. Photons of light lose energy according to a neutral-light process, in which the loss of energy is an intrinsic consequence of the characteristics of the medium related to the free electron density, through which the photons travel. It has been largely discussed in another video. Please check the video description. Indeed, galaxies and clusters of galaxies produce free electrons in the interstellar medium as a result of the photoionizations of H1 regions, and push them to the intergalactic medium driven by stellar winds and magnetic fields. The Hubble constant, in Thalight terms, is a constant only in respect to the environment that we are investigating. It assumes different values depending if we are considering the intergalactic medium or the interstellar medium. The variation is even much stronger in the interstellar medium itself the closer we move toward a stellar corona as the distribution of free electrons increases. It is expressed by the redshift anomalies in the solar corona. These anomalies lead to the so-called Hubble tension, which, in mainstream terms, is explained through the expansion of space. Again, it is only a pure mathematical argument. From the radiative transfer equation, we can write the variation of the intensity along the path traveled by the photons is directly proportional to the intensity itself. The minus sign indicates that the radiation decreases for increasing distances through the absorption coefficient. We can calculate that intensity decreases according to a decreasing exponential law for increasing distances. Moreover, we have a clear analogy between absorption coefficient and the density of targets in the medium multiplied by the interaction cross-section as follows. The term at the numerator is the intensity of radiation emitted by the source described by the Planck spectrum. An observer far away in space will see a different frequency respect to those emitted by the source. In detail, the observed frequency at distance r results in a smaller value with respect to the emitted frequency by the source. It is mathematically expressed by this expression. Or namely, the observer measures a redshift, a shift of the stellar absorption lines towards lower energies. It has largely been discussed and calculated in the neutral light theory in a non-expanded universe, according to the following expression. From this equation and from the definition of the redshift in the light spectrum, after some mathematical steps, we can extract the frequency detected by the observer as follows. Moreover, if we now consider the contribution provided by all stars, the total intensity at the observer can be expressed by the integral along the distance as follows. The electron density in the intergalactic medium, exactly equal to that between stars in the galaxy in the interstellar medium, is 0.5 electron each cubic meter. The corresponding Hubble constant in the intergalactic medium, according to the neutral light theory, which is now only function of the properties of the electron, is equal to the following expression. After many mathematical steps, the final expression of the total intensity detected by an observer is the following, where Z is a variable function of the constants in the Planck spectrum, together with the star temperature as well as the observed frequency. A is a parameter expressing the diameter of the targets through their geometrical cross-section. X is a variable varying with the distance source to the observer, r, and a function of the parameter z. Capital R is the Einstein's radius of the universe from his first general relativity paper. This vanishes in the mathematical steps. We want to determine the value of the parameter z containing the observed frequency which maximizes the spectrum. Therefore, we derive the spectrum with respect to this variable, expanding it for the parameter A according to a Maclaurin series and setting it equal to 0. We are expanding the derivative with respect to z, not the space. After very long mathematical steps, we obtain a relation between the max frequency observed and the parameter A, function of the diameter of the targets. We can stress out that the frequency peak obtained has to be exactly equal to the frequency peak of the Planck spectrum describing a black body, detected from a terrestrial observer. By equating the two equations, we obtain that after several mathematical steps, that the diameter of the target producing a black body spectrum at 2.725 Kelvin is directly proportional to the Hubble constant and inversely proportional to the density of the targets. Moreover, there is a relation with the ratio between the CB temperature and the temperature of the source emitting the main source of the radiation, which interacts with the targets. We can remind that the star class M, dwarfs, is the most abundant in the Milky Way. Due to that, we can assume it as a criterion for the abundances of stars in an average spiral galaxies in the universe. This is because spiral galaxies are the most common galaxy type in the universe. If we assume star-like sources of this kind, as their surface temperature varies in the range 2000–3500 Kelvin, we can accordingly calculate an average surface temperature as shown in the formula. The average density of the dust grains can be calculated as follows, considering magnetite the most dominant component. Due to this, inserting these values in the previous formula, we obtain an average diameter of the targets in space equal to the following expression. As it is not a coincidence that the diameter of the targets and their densities match respectively the order of magnitude micrometer, exact size between 10 and 1000 micrometer, as well as the chemical density of the cosmic dust grains observed in space, therefore, the cosmic dust really represents our research space matter that emits a thermal radiation in equilibrium with the redshifted starlight. It is an absolute result valid for any observer in any location, whether an observer is in our galaxy, in a galaxy of the local group, or in any other galaxy in the cosmos. We focus on cosmic dust grains in the intergalactic medium and interstellar medium, which fall exactly within the found range of diameter 10–1000 micrometers, orbiting the Earth and recently reported in detail by an important scientific study conducted by the Antarctica expedition. Moreover, this study shows that due to the resistance that the Earth's atmosphere exerts against the falling grains, their diameter found on Earth slightly decreases. Furthermore, dust has been detected on comets by recent space missions and reveal a diameter size up to 500 micrometers, confirming their presence and most likely also their origin within the solar system. At a distance of less than 1 light-year, at the border of our solar system, an important astronomical zone has been postulated, the Oort cloud. It is a spherical shell which embeds the solar system and defines its boundaries. It includes the orbital trajectory of all comets as deduced by the calculation of their long orbital period. As demonstrated, the CMB can be interpreted as a thermal radiation in the interstellar medium from cosmic dust grains in equilibrium with the redshifted starlight. The dust grain, between starlight sources in the interstellar medium, physically surrounded by the smallest electron density, behave like their parents in the far intergalactic medium. Their electron density is 0.5 electron each cubic meter. Moreover, the dust grains closer to the sources of radiation in the galaxy, mainly stars, behave differently, showing a greater range of thermal emission in infrared with temperatures up to 27 Kelvin. Basically, the closer the dust grains are to the source of radiation, like stars, the more the grains are heated up. Indeed, we measure a range of temperature between 15 and 27 Kelvin in the Milky Way. The farther from the source the dust grains are in space, the less they are heated up, and accordingly, they find an equilibrium temperature with the environment. Now, there is a relation between proximity to the source and the free electron density. Close to the star, we have an electron density that can reach 10 to the 12 electrons each cubic meter, and a temperature of 7000 Kelvin. Far away in the intergalactic medium, but also between stars in the interstellar medium, we measure 0.5 electrons each cubic meter, and a temperature of 0 Kelvin, so corresponding to the absolute zero, as there are no sources there. Therefore, the electron density also expresses a distance in space from the source. Far away in space, in an intergalactic medium, there are no sources and the electron density is really small. Therefore, the cosmic dust there is thermalized and the temperature that we measure is exactly the 2.725 Kelvin.